The wind never quit on the Kansas prairie. Hans K. learned that his first winter in central Kansas in 1886 when his cabin roof lost an entire corner section in a spring gale, exposing his family to driving rain and forcing an emergency rebuild. He had built his roof exactly the way every settler was told to build it. Single-layer wood shakes on widely spaced rafters, fast and cheap, the frontier standard. Across the windswept plains that season, dozens of homesteaders fought the same losing battle as their roofs lifted, cracked, and failed in prairie gusts. The local foreman carpenter mocked Hans when he quietly began combining techniques from his German training with bark sheet methods borrowed from plains tribes to create what neighbors called his impossible triple-layer roof design. Then came the tornado of June 1887. What did this immigrant understand about wind and layers that destroyed every other roof but left his untouched? The open prairie stretched endlessly in every direction from Hans K.'s homestead claim. A sea of grass broken only by scattered cottonwoods along the creek bottoms and the occasional sod house or timber claim shack dotting the horizon. Central Kansas in 1886 offered settlers little natural shelter from the relentless winds that swept across hundreds of miles of flat terrain, gathering force and fury as they rolled eastward from the Rocky Mountain foothills. The landscape demanded speed in construction above all else. Families needed shelter before the next storm season, before winter, before their limited cash reserves ran dry paying for supplies hauled in by railroad from distant lumber mills. Every homesteader in the county knew the accepted method for cabin roofing because it made perfect sense for frontier conditions. Cedar or pine shakes, split or sawn at the nearest mill, went up fast when laid in a single layer across rafters spaced 3 to 4 feet apart on center. A crew of 3 men could frame and shake an entire roof in 2 days if they pushed hard, and the materials cost stayed reasonable even after the railroad freight charges. The wide rafter spacing meant fewer heavy timbers to buy and haul, while the single shake layer kept the weight down and the nail count manageable. For most weather, the system worked well enough. Hans had followed this exact method when he built his first cabin that spring, trusting the collective wisdom of men who had been homesteading the Kansas prairie for a decade or more. The local foreman carpenter, a weathered man named T, who had supervised dozens of cabin builds across 3 townships, assured Hans that single-layer shakes on wide rafters represented the perfect balance of cost, speed, and durability for prairie conditions. T had built his own reputation on delivering functional shelter quickly and cheaply, and his methods reflected the harsh economics of frontier life where time meant survival and every dollar spent. On excess materials was a dollar not available for seed, livestock, or emergency supplies. But the prairie wind tested every structure differently than the sheltered valleys where many of these building methods had originated. The Schneider cabin, built just 2 miles south using the standard approach, lost half its shake covering in a late April windstorm that spring, leaving the family scrambling to collect scattered roof pieces across a quarter section of grassland. The Morrison place suffered worse damage when sustained gusts of 40 miles per hour caught the underside of loosely fitted shakes, creating enough uplift pressure to crack 2 rafters and peel away an entire section of roofing. The exposed interior took water damage that ruined stored grain and forced an expensive emergency repair using materials that had to be freighted in from Topeka at premium rates. Hans possessed knowledge that set him apart from most Kansas settlers, though he had initially chosen to ignore it in favor of fitting in with local practices. His apprenticeship in the German carpentry guilds had taught him heavy timber joinery techniques developed for the windy mountain regions of Bavaria, where structures face similar uplift forces and lateral loading. German building tradition emphasized redundancy, layered protection, and engineering for the worst possible conditions rather than average weather. During his journey west, Hans had also observed Native American building techniques in wooded regions, particularly the use of overlapped bark sheets as weather barriers and wind seals on traditional dwellings. These knowledge sources created a different perspective on the roofing problem, one that prioritized long-term performance over immediate cost savings. Hans began to see the standard frontier method not as the optimal solution, but as a dangerous compromise that worked only until it failed catastrophically. The German approach would call for closer rafter spacing, heavier timber dimensions, and multiple protective layers to distribute loads and provide backup systems. The indigenous techniques suggested that bark could serve as an effective intermediate layer between structural elements and exterior weather surfaces. When Hans quietly mentioned these alternative approaches to T and other local builders, the reaction was swift and dismissive. "That German will overbuild again," T warned other settlers within Hans's hearing. "What kind of fool uses 3 layers of shakes and bark for a little frontier cabin roof? You'll spend more on roofing than most men pay for their entire claim." The criticism reflected genuine concerns about resource allocation in a cash-poor economy, but it also revealed the frontier mentality that equated any deviation from accepted practice with wasteful excess. Local suppliers reinforced this skepticism when Hans inquired about purchasing additional rafters, extra shakes, and metal flashing materials. The lumberyard operator in the nearest railroad town calculated that Hans's proposed design would require roughly double the standard material quantities, extending the construction timeline from 2 days to perhaps 10 or 12 days, and increasing the roof cost from approximately $40 to nearly $80. "You'll never recover in crop yields what you waste in roof," he told Hans bluntly. "Every day you spend overbuilding is a day not spent breaking sod or tending livestock." Despite this pressure to conform, Hans's direct experience with roof failure convinced him that the conventional wisdom carried hidden costs that exceeded the upfront savings. His own emergency repair had consumed 3 full days of critical spring planting time, plus the expense of replacement materials and the stress of exposing his family to weather during repairs. He calculated that similar failures across the region were costing settlers far more in aggregate than the extra materials required for proper initial construction would have cost. Hans decided to test his theory systematically, beginning with partial modifications to see how traditional techniques would perform under prairie conditions. He committed to spacing his rafters closer together, using heavier timber dimensions, and adding at least one intermediate layer between the structural elements and the exterior shakes. This represented a compromise between full German guild standards and frontier economics, but it would provide measurable data on whether traditional craft knowledge could outperform the accepted lightweight method when prairie winds push structural systems to their limits. The principle at stake extended beyond roofing techniques to encompass a fundamental question about frontier building philosophy. Hans believed that a well-engineered roof system, built by hands-on craft with redundant layers and close spacing, would outperform the accepted lightweight method not just in extreme weather, but in overall long-term value, when repair costs, downtime, and replacement cycles were factored into the economic equation. Hans found his first teacher in structural engineering through necessity rather than choice. Gustav M., a German journeyman carpenter who had settled near Grand Island, Nebraska, arrived in central Kansas that summer, hauling lumber for a massive barn project on the Hendricks Spread. Gustav had learned his craft in the Black Forest region, where winter snow loads and mountain winds demanded timber framing that could resist forces from multiple directions simultaneously. When Hans approached him with questions about rafter sizing and spacing, Gustav walked him through the mathematics of load distribution with the patience of a man who understood that improper framing killed people. The standard frontier rafter system used 2 by 6 inch timbers spaced 3.5 to 4 feet apart on center, a configuration that worked adequately for static loads like snow or the weight of the roof itself. But Gustav explained how wind-up lift created entirely different stress patterns that transformed rafters from simple beams into complex structural elements fighting lateral and rotational forces. "Wind gets under your shakes, pushes up," Gustav demonstrated with his hands. "And now your rafter is not holding roof down, it is being pulled apart at the connections. The wider you space them, the more leverage the wind has to work with." Gustav's solution involved reducing rafter spacing to 2.5 feet on center while increasing the timber dimensions to 4 by 8 inches. This change created a network effect where each rafter shared loads with its neighbors instead of fighting forces independently. The closer spacing meant that any uplift pressure got distributed across multiple support points rather than concentrating on individual weak links. The heavier timber dimensions provided greater resistance to bending and splitting under stress, while the increased mass helped counteract uplift forces through simple physics. But Gustav's most important innovation was the integration of collar ties and diagonal bracing to create what he called load paths. Collar ties, horizontal beams connecting opposite rafters at their midpoints, prevented the roof from spreading outward under load. Diagonal braces, angled supports running between rafters and connecting to the ridge beam, created triangular configurations that distributed forces throughout the entire roof structure. You make the roof work like one piece, not like many pieces fighting each other, Gustav explained as he sketched the configuration in the dirt beside Hans's foundation. The practical application required precise joinery techniques that differed significantly from standard frontier carpentry. Each collar tie had to be notched into its rafters and secured with both nails and wooden pins to prevent movement under stress. The diagonal braces demanded careful angle cuts and tight-fitting joints that would not loosen over time. Gustav showed Hans how to mark and cut these connections using traditional German measuring techniques that relied on proportional relationships rather than exact measurements, ensuring that the entire framework would function as an integrated system. Hans's second structural teacher emerged from local disaster. Ezra Thompson had built his dairy barn using the conventional wide-spaced rafter system, but when a severe thunderstorm struck in early summer with sustained winds of 35 to 40 miles per hour, the uplift forces literally pulled his roof framework apart. Hans arrived the morning after the storm to find Thompson standing amid the wreckage, studying the failed connections with the intensity of a man whose livelihood depended on understanding what went wrong. Thompson's analysis revealed the specific failure mechanisms that Gustav's theories had predicted. The wide rafter spacing had allowed wind pressure to build up under the roof, sheathing, creating a lifting force that exceeded the holding power of the nails connecting rafters to the wall plates. Once one rafter pulled loose, the failure cascaded across adjacent sections, as the remaining structure tried to carry loads it was never designed to handle. Thompson pointed to splinters of wood still embedded in bent nails, evidence of the violent forces that had torn his carefully built barn apart. This direct observation of structural failure provided Hans with crucial data about the load limits of conventional frontier framing. Thompson estimated that his barn had cost him nearly $60 in materials and 8 days of labor to build initially, but the storm damage would require another $40 and 6 days to repair properly. More importantly, the destroyed stored hay represented a loss of winter feed worth approximately $30, creating total storm damage of $70 against an original investment of $60. Hans began his own framing work in early August, laying out rafters at the 2.5-foot spacing Gustav had recommended. The 4x8-inch timbers required more careful handling than standard lumber, but their additional mass and strength became apparent immediately. Where a 2x6-inch rafter would flex noticeably under the weight of a man, the 4x8-inch beams remained rigid and stable. Hans could walk across the framework without experiencing the springy deflection that characterized most frontier roof systems. The installation of collar ties and diagonal bracing transformed the individual rafters into a cohesive structural network. Hans cut each collar tie from 2x8-inch stock and notched the connections precisely according to Gustav's specifications. The diagonal braces, crafted from 2x4-inch material, created triangular supports that tied each rafter to its neighbors and to the central ridge beam. As each connection was completed and secured, the entire framework became progressively more rigid and stable. The construction timeline extended from the standard 2 days to nearly 10 days, but Hans could measure the structural improvements objectively. He tested the framework's deflection by placing a straight board across several rafter bays and measuring any movement when additional weight was applied. The standard system typically showed deflections of 1/2 inch or more under moderate loads, while Hans's heavy framework showed less than 1/8 inch of movement under the same conditions. When sustained winds of 25 miles per hour struck the area in late August, Hans's framework provided the first real-world test of Gustav's engineering principles. The collar ties prevented any spreading motion at the wall plates, while the diagonal braces transferred wind loads efficiently throughout the structure. Hans measured the deflection using a plumb line suspended from the ridge beam and found that his system moved less than 1/4 inch even during the strongest gusts, compared to nearly 2 inches of movement in Thompson's hastily rebuilt barn roof. The structural foundation was now in place for the envelope systems that would complete Hans's integrated approach to prairie wind resistance. The weakness in every shake roof lay not in the shakes themselves, but in the spaces between them, gaps that created pathways for wind infiltration and pressure buildup beneath the roofing surface. Hans discovered this principle through careful observation of damaged neighbors' roofs, where he could trace the failure patterns back to specific points where wind had penetrated the envelope and begun the destructive process of lifting individual shakes from their fastenings. Understanding this vulnerability led him to seek knowledge about membrane systems and layered protection from sources beyond conventional frontier carpentry. His teacher in envelope sealing came from an unexpected direction. Joseph Crow Feather, a Plains Osage craftsman who had worked on various homestead projects throughout the territory, possessed generations of accumulated knowledge about bark sheet roofing techniques developed for the variable weather patterns of the Great Plains region. Joseph had observed the consistent failures of single-layer shake systems and offered to demonstrate how overlapping bark sheets could create an intermediate membrane that blocked wind infiltration while adding protective mass to resist uplift forces. The bark sheet technique required specific timing and material selection that differed entirely from conventional lumber-based construction. Joseph explained that oak and hickory bark could be harvested only during late spring and early summer, when the sap flow allowed large sheets to be peeled intact from the trees. The optimal sheets measured approximately 2 feet wide by 6 to 8 feet long, with thickness uniform enough to lay flat but substantial enough to resist tearing under wind stress. Joseph demonstrated the harvesting process using a specialized technique that involved scoring the bark in vertical lines and carefully working it free from the trunk using wooden wedges and patient manipulation. The installation of bark sheets demanded an understanding of overlap patterns and water management that reflected decades of practical experience with prairie weather conditions. Joseph showed Hans how to begin each course at the eaves and work upward, overlapping each sheet by 6 to 8 inches to ensure that water would flow downward without finding horizontal pathways into the underlying structure. The bark had to be positioned while still somewhat flexible from recent harvesting, as dried bark became brittle and difficult to manipulate into the compound curves required for proper roof installation. Hans's second teacher in layered envelope systems was Lars Johansson, a Norwegian immigrant who had arrived from Minnesota with experience in sod roofing techniques adapted to harsh winter conditions. Lars explained how Scandinavian builders had developed multiple layer systems to handle both heavy snow loads and the thermal cycling that caused single-layer systems to fail over time. His approach emphasized the principle of redundant protection, where each layer served a specific function while providing backup for the layers above and below. Lars demonstrated how the sequence of installation determined the effectiveness of the entire system. The first layer consisted of conventional shakes installed directly over the sheathing, but with reduced exposure of 4.5 inches instead of the standard 5.5 inches. This tighter overlap created the primary weather barrier while providing a secure base for the subsequent layers. The bark sheets went on next, overlapped and positioned to shed water, while creating an air seal that prevented wind from reaching the primary shake layer. The final outer layer of shakes served as the sacrificial surface that took the direct impact of weather while protecting the membrane and structural elements beneath. Lars emphasized that this outer layer needed to be installed with slightly different fastening patterns than conventional roofing, using longer nails that penetrated through all layers and into the underlying sheathing to create mechanical connections that could resist the combined uplift forces acting on the complete assembly. The mathematical principles governing the layered system revealed why single-layer approaches failed consistently under prairie wind conditions. Hans calculated that his 3-layer assembly would weigh approximately 18 to 20 pounds per square foot, compared to the standard 5 to 7 pounds per square foot for conventional single-layer systems. This additional mass created a gravitational resistance to uplift that increased proportionally with wind speed, while the sealed envelope eliminated the pressure differentials that created uplift forces in the first place. Hans began the envelope installation in early September, working systematically from eaves to ridge to ensure proper water management throughout the system. The bark sheets required careful handling to prevent cracking during installation, and Hans developed a technique of slightly dampening the bark to maintain flexibility while positioning each piece. The overlap patterns created a continuous membrane that effectively sealed the roof surface while allowing for thermal expansion and contraction through the seasonal cycles. The installation process revealed the importance of fastener selection and placement in multi-layer systems. Standard frontier practice used common nails driven flush with the shake surface, but the three-layer assembly required longer galvanized nails that could penetrate through all layers without creating stress concentrations that might lead to splitting or pull-through failures. Hans used a combination of 8-penny and 10-penny nails selected based on the total thickness at each fastening point. When the first significant wind test arrived in mid-September with sustained speeds of 30 to 35 miles per hour, Hans could observe the performance differences between his system and conventional installations in real time. His neighbor's single-layer roof experienced visible lifting and flutter as wind pressure built up beneath individual shakes, creating the characteristic rippling motion that indicated the onset of failure. Hans's three-layer system remained motionless and solid, with no visible deflection or movement even during the strongest gusts. The quantifiable results exceeded Hans's initial projections for system performance. Temperature measurements inside his cabin during the wind event showed that the sealed envelope maintained interior conditions more effectively than conventional construction, with temperature variations of less than 3 degrees compared to swings of 8 to 10 degrees in neighboring cabins where wind infiltration created drafts and heat loss. The multi-layer system had created not just structural protection, but thermal performance improvements that would translate into reduced fuel consumption throughout the heating season. Hans's bark sheet membrane had transformed the roof from a collection of individual components into an integrated envelope system that managed both structural loads and environmental conditions through engineered redundancy rather than hoping single-layer protection would prove adequate under extreme conditions. The vulnerability of even the best-designed roofing system lay in its connection points, where individual components transferred loads to the underlying structure and where water could find pathways through the envelope. Hans understood that his heavy framing and multi-layer approach would fail without proper attachment methods and continuous sheathing that eliminated the weak points that destroyed conventional frontier roofs. The search for expertise in fastening and sealing led him to sources with military engineering experience and practical metalworking knowledge. His teacher in systematic attachment came from Captain Robert Sterling, a retired United States Army engineer who had supervised the construction of frontier outposts throughout Kansas and Nebraska during the Indian Wars. Sterling had observed the catastrophic failure of military buildings under prairie wind conditions and had developed attachment protocols that prioritized redundancy and load distribution over speed of construction. His experience included the analysis of multiple roof failures at Fort Larned and Fort Dodge, where inadequate sheathing and insufficient fastening had resulted in complete structural loss during severe weather events. Sterling explained that conventional frontier sheathing created systematic weak points that guaranteed eventual failure under wind loading. The standard practice of laying sheathing boards with gaps of 3 to 4 inches between them allowed wind pressure to build up in the enclosed spaces beneath the roofing materials, creating the uplift forces that pulled shakes loose from their fastenings. Sterling demonstrated this principle by showing Hans how air pressure differentials worked on both sides of a roof surface, explaining that gaps in sheathing essentially created internal wind tunnels that amplified external weather conditions. The military solution involved continuous sheathing using full-width boards laid edge to edge with no gaps between them. Sterling specified 2 by 6 inch boards, installed perpendicular to the rafters, and nailed at every rafter intersection, with at least 3 nails per board per rafter. This created a solid platform that eliminated internal air spaces, while providing a secure fastening base for the roofing materials above. The continuous sheathing also distributed loads more evenly across the rafter system, preventing the concentration of stress at individual fastening points that led to pull-through failures. Sterling's attachment methodology addressed the specific challenges of securing multiple roofing layers through a systematic approach to fastener selection and placement. The bottom layer of shakes required 8-penny galvanized nails driven through the sheathing and into the rafters, with each shake secured by at least 2 nails positioned 1 inch from each edge and 6 inches from the bottom. The bark membrane layer needed different fasteners entirely, using broad-headed roofing nails that distributed load across the bark surface without creating stress concentrations that might tear the organic material. The outer shake layer demanded the most sophisticated fastening approach, requiring 10-penny galvanized nails long enough to penetrate through all three layers and achieve solid purchase in the underlying sheathing. Sterling emphasized that these nails had to be driven at slight angles to create mechanical interlocking that would resist both uplift and lateral forces, while the nail heads needed to be countersunk slightly below the shake surface to prevent wind from catching the fastener heads and creating additional uplift points. Hans's second teacher in attachment systems was Heinrich Zimmermann, the local blacksmith who had developed expertise in sheet metal work and weatherproofing through years of repairing damaged buildings throughout the county. Zimmermann understood that even perfect sheathing and fastening would fail without proper flashing at the critical junction points where different roof surfaces met and where the roofing system connected to walls and other structural elements. Zimmermann's approach to flashing reflected both practical frontier constraints and sound engineering principles developed through direct observation of failure patterns. He had salvaged sheet tin from various sources, including shipping containers and damaged farm equipment, forming custom flashing pieces using basic metalworking tools and techniques adapted to the specific requirements of Hans's three-layer system. The flashing had to accommodate the increased thickness of the multi-layer assembly while providing continuous protection at ridge lines, valleys, and eave connections. The ridge flashing required particular attention because the peak of the roof created the most vulnerable point for wind penetration and water infiltration. Zimmermann fabricated ridge pieces from 14-gauge tin sheet, forming them into channels that extended at least 6 inches down each roof slope while providing a weather-tight seal over the uppermost course of shakes. Each piece overlapped its neighbor by at least 4 inches, with the joints sealed using pine pitch mixed with ground charcoal to create a flexible waterproof compound that could accommodate thermal expansion and contraction. The eave flashing presented different challenges because it had to manage both wind uplift, prevention, and water drainage while accommodating the varying thickness of the three-layer system. Zimmermann created custom eave strips that extended from the fascia board up under the first course of shakes by at least 8 inches, with the metal formed into a slight upward curve that would direct any wind-driven water back toward the exterior rather than allowing it to penetrate horizontally under the roofing materials. The installation sequence for the complete attachment system required precise coordination between sheathing, flashing, and fastening operations. Hans began with the continuous sheathing, ensuring that each board was properly secured to every rafter crossing before proceeding to the flashing installation. The eave flashing went on first, followed by the valley flashing where roof sections intersected, with the ridge flashing saved for last to ensure proper overlap relationships throughout the system. The fastening of the roofing layers followed Sterling's systematic approach, beginning with the base shake layer secured directly to the continuous sheathing. Hans used a chalk line to ensure straight courses and consistent overlap, driving each nail at the precise angle Sterling had specified to maximize holding power while avoiding splits in the shake material. The bark membrane layer required different techniques, with broad-headed nails driven through pre-punched holes to prevent tearing during installation. The outer shake layer demanded the most careful attention to fastening patterns, because these fasteners had to secure the entire three-layer assembly while resisting the maximum wind loads. Hans developed a rhythm that ensured consistent nail placement and penetration depth, checking frequently with a small gauge block to verify that each nail achieved proper embedment in the underlying sheathing without overdriving and damaging the shake surface. When the complete attachment system was tested by a sustained wind event in early October with gusts reaching 40 miles per hour, Hans could observe the performance advantages of systematic fastening and continuous sheathing. His neighbor's conventional roof experienced visible movement and flutter at individual shakes, indicating that fasteners were approaching their load limits and beginning to work loose in the sheathing. Hans's system showed no visible movement or deflection, with the continuous sheathing and redundant fastening distributing loads so effectively that no individual connection point experienced critical stress levels. The temperature control benefits of the sealed sheathing system became apparent during the first cold nights of autumn when Hans measured interior temperatures that remained stable within 2 degrees, while neighboring cabins experienced temperature swings of 6 to 8 degrees as wind infiltration carried away heated air through gaps in conventional sheathing systems. The atmospheric conditions on June 15, 1887, created the perfect combination of factors for generating destructive wind phenomena across central Kansas. A sharp temperature differential between hot surface air and cooler upper atmospheric layers, combined with wind shear from conflicting directional flows, produced the rotating circulation patterns that meteorologists would later identify as mesocyclonic activity. The resulting windstorm moved across the county as a narrow band of destruction approximately half a mile wide, with peak wind speeds estimated at 70 to 80 miles per hour, and sudden pressure drops that created additional stress on any structure in its path. Hans observed the approaching storm from his cabin doorway as the characteristic wall cloud formation moved eastward across the prairie, its dark rotation visible against the lighter sky behind it. The barometric pressure drop preceding the storm created an eerie stillness that experienced plainsmen recognized as the harbinger of violent weather, followed by the distinctive roar that indicated winds of exceptional velocity approaching their location. Hans had approximately 10 minutes to secure loose items and take shelter before the storm's full fury struck his homestead. The aerodynamic behavior of different roofing systems under extreme wind conditions revealed principles that conventional frontier construction had never been designed to address. Single-layer shake roofs experienced what engineers would later term flutter and resonance effects, where individual shakes began vibrating in harmonic patterns that amplified the destructive forces acting upon them. The wide spacing of conventional rafters allowed entire sections of roofing to act as lifting surfaces, creating airfoil effects that generated tremendous uplift forces as wind velocity increased beyond 30 miles per hour. Hans's integrated system responded differently to the same aerodynamic stresses, because the continuous sheathing and multi-layer construction eliminated the air spaces that created pressure differentials in conventional roofing. The sealed envelope prevented wind from penetrating beneath the roofing surface, while the additional mass of the 3-layer assembly provided inertial resistance to the sudden pressure changes that characterized tornado-level wind events. The close rafter spacing distributed loads so effectively that no individual component experienced stress concentration sufficient to initiate the catastrophic failures that destroyed neighboring structures. The Morrison cabin, located 300 yards southeast of Hans's homestead, provided a direct comparison of system performance under identical wind conditions. Built using standard frontier methods with 2 by 6-inch rafters, spaced 42 inches on center and single-layer cedar shakes, the Morrison roof began failing within minutes of the storm's arrival. Hans watched from his window as individual shakes started lifting and fluttering, creating the cascade effect where each loose shake increased the vulnerability of its neighbors by disrupting the intended overlap patterns and exposing larger areas to wind penetration. The complete destruction of the Morrison roof occurred in stages that demonstrated the progressive failure mechanisms built into conventional construction methods. The initial shake losses created entry points for wind penetration beneath the remaining roofing surface, generating internal pressure that pushed upward against the underside of intact sections. When the uplift forces exceeded the holding power of the nails, securing rafters to the wall plates, entire rafter sections pulled loose and became airborne projectiles that caused secondary damage to neighboring structures. The Hendricks Place, built with slightly heavier construction using 2 by 8-inch rafters, but still employing single-layer roofing and gapped sheathing, experienced partial failure that illustrated the importance of envelope integrity under extreme conditions. Approximately 60% of their roof remained attached, but the sections that failed created openings that allowed rain and debris to destroy stored grain and household possessions worth an estimated $45. The family spent the following 6 weeks living in their storm cellar while reconstructing the damaged portions of their home. Hans's measurement of his own system's performance during the storm provided quantifiable data about the effectiveness of integrated design principles under maximum stress conditions. Using a plumb line suspended from the ridge beam, he recorded maximum deflections of less than 1/4 inch, even during the most violent periods of the storm. The temperature inside his cabin remained stable at 74 degrees Fahrenheit throughout the event, compared to outdoor readings that fluctuated between 68 degrees during the pressure drop and 86 degrees immediately after the storm passed. Secort's economic analysis of storm damage across the affected area revealed the hidden costs of conventional construction methods when subjected to their design limits. The 5 families who lost complete roofs faced reconstruction costs averaging $55 each in materials plus 30 to 35 days of labor per family. The 2 families with partial roof damage required an average of $28 in materials and 18 days of labor for repairs. Hans's total storm damage consisted of 1 broken shake that required 15 minutes to replace using materials he had stored for routine maintenance. The psychological impact of system failure extended beyond immediate economic losses to include the disruption of daily routines and the stress of living in damaged structures during reconstruction. The families with roof damage reported sleep difficulties, increased illness among children, and depression among adults who felt overwhelmed by the magnitude of required repairs. Hans's family experienced no disruption to their normal routines and actually assisted neighboring families by providing temporary shelter and storage for salvaged possessions. Word of Hans's roof performance spread throughout the county through the informal communication networks that connected scattered homesteads across the prairie. Within 2 weeks of the storm, 3 experienced carpenters had visited Hans's cabin to examine his construction methods and ask detailed questions about material specifications and installation techniques. Samuel Richardson, a barn builder operating across 4 counties, hired Hans as a consultant for a major grain storage facility being constructed near Hutchinson, Kansas. The adoption of Hans's techniques accelerated as the practical benefits became apparent through direct comparison with conventional methods. By autumn of 1888, local lumber yards reported increased demand for heavier rafter stock and longer nails suitable for multi-layer roofing systems. The railroad depot at the county seat began stocking sheet metal flashing materials that had previously been available only through special order, indicating widespread acceptance of advanced weatherproofing techniques. The knowledge transfer process occurred through apprenticeship relationships rather than formal documentation, reflecting the oral tradition that characterized frontier craftsmanship. Young carpenters working with established builders learned Hans's framing and envelope techniques as standard practice rather than innovations, ensuring that the methods would persist beyond the career of any individual practitioner. By 1890, the regional building tradition had incorporated continuous sheathing, close rafter spacing, and multi-layer roofing as normal specifications for structures intended to withstand prairie weather conditions. The long-term validation of Hans's approach became apparent through the survival rates of structures built, using his methods compared to conventional frontier construction. A survey conducted 20 years later found that 87% of buildings constructed with heavy framing and multi-layer roofing remained in serviceable condition, while only 31% of conventionally built structures from the same period had avoided major repairs or complete replacement.